In this video, we're going to continue our discussion of iteration and in particular introduce the iterator type. We've seen that loops support iteration over collections, and iteration is a very important programming pattern. We use it a lot in solving problems. One of the difficulties is that implementation differences amongst collections can make it hard to write efficient general solutions to tasks involving iteration. And we've seen in a previous video that removing items during iteration can be problematic and error-prone. The iterator type offers both efficient and safe iteration over all types of collection, be that array list, linked list, or one of the other collection types typically found in the java.util package. Each collection provides a collection-specific iterator type. The iterator type is interesting because each collection provides its own collection-specific implementation of that type. However, the iterator abstraction, or in other words, the way that we use an iterator object, is consistent across all collection types. So let's look at some basics of how we make use of an iterator when we want to iterate over a particular collection. All of the collection types have a method called iterator. Note that because it's a method, it starts with a lowercase I, and that method returns an object of type iterator, where in this case the type starts with an uppercase I. The iterator type is a generic type, just like the collection types are, and so strictly speaking what the collection returns is something of type iterator of, where the type of the iterator is based upon the type of objects that the collection is storing. In this video we're going to consider three methods that the iterator type provides. The first method is called hasNext. It takes no parameters and returns a Boolean value. The second method is called next, which again takes no parameters and returns an object of type e, where e is the type of the object stored within the collection that the iterator is going to operate over. And finally, the third method is called remove, which again takes no parameters and does not return a result. This is the typical way in which we would request an iterator object from a collection and then make use of the object once we have it. The first step is to call the iterator method on the collection that we wish to iterate over, and that will return an iterator object typed according to the type of objects stored within the collection. So that will be the type that goes between the angle brackets after the word iterator. The way that we use an iterator is to repeatedly ask it whether there are any more items in the collection to be examined, and as long as it returns true from the hasNext method, we can then continue the iteration and request the next item from the iterator. So the typical pattern is to say, while the iterator is returning true from its hasNext method, go and retrieve the next item by calling the iterator's next method, store it into a variable of the appropriate type, that is the type of the objects stored within the collection, and then we're going to do something with that object that's just been returned. And then that process repeats. So we always want to protect a call to the next method with a preceding call to ask the iterator whether it has another item to return. We'll take a look at the internal mechanics of how an iterator manages telling us whether there are any more items or not and then returning them shortly. What we see here in outline is a consistent pattern that we'll use over and over again whenever we use an iterator to iterate over a collection. We request an iterator object and then repeatedly ask the iterator whether there are any more items to be returned. If it replies true, then we'll request the next item and process it. An important point to notice about the body of the loop is that we do not interact directly with the collection inside the body of the loop. all of our interactions with the collection will be via the iterator. If we were to try and remove an item or add further items to the collection directly via the collection, then we would receive a concurrent modification exception. So that's not permitted. Here's a practical example of the list all files method now coded to use an iterator. Notice that we see reproduced exactly the pattern that we saw on the previous slide. We're requesting from the tracks collection an iterator object, and the type of the object returned is iterator of track. We ask the iterator whether there are any more tracks to process, and if it replies true, we go and get the next track, and then we do something with the track, in this case printing out the details. We'll see some more examples shortly, but let's think about and try and understand the mechanics of how iterators work, because that will give a better understanding for how to use the hasNext and next methods. So here's a visualization of what we might see as being a collection of objects of type element. And our goal is to iterate over all of those items that are stored in the collection. So we request from the collection an iterator object. So we invoke the iterator method on the collection, and it's going to return us an iterator object. So we'll most likely use that call to the iterator method by storing the result into a variable whose object is type iterator over the appropriate type. The next step is to ask the iterator whether there are any more items in the collection that we haven't yet processed. So we call the hasNext method. And if the hasNext method returns true, then we know it's okay to invoke the next method, and the result of that will be that the iterator returns us a reference to the object that it was referring to. Now, an important point to notice about the animation is that it shows that as well as returning a reference to the object it was referring to, the iterator moves on within the collection to the next item in the collection. So it's important to appreciate that making a call to next is something we can only do once for any particular item in the collection. Once we've called next on an iterator, the iterator will move on to whatever follows that item inside the collection. We can never go backwards with the iterator and revisit an item that it previously returned to us. So note the mechanics as the following slides illustrate that point several times. So again, we can ask the iterator whether there are any more items that we haven't processed yet. If it returns true, then we call next. We get a reference to that next object, and again the iterator object moves on internally within the collection. The mechanics of how the iterator is working out where to be within the collection will depend upon the type of the collection that the iterator is working on. And the details of that are hidden via abstraction. We don't need to know the details of how an iterator might work with an array list or a linked list or one of the other collection types within the java.util package. It's sufficient to know that we interact with an iterator object in exactly the same way, regardless of what type of collection we're iterating over. So the pattern that we're using of calling hasNext and next will apply in cases of every type of collection that we want to iterate over. Once again, we can ask the iterator whether there are any more items to be returned. If it replies true, then we go and ask for the next item. We get a reference to that item. The iterator moves on. We can ask it again, are there any more items? Again, it's going to reply true, so we can call next and get a reference to the next one. So we're gradually progressing our way through the collection, item by item, in sequence from the beginning to the end of the collection. Now we notice that the iterator has delivered the final item within the collection, and it's no longer referring to an item in the collection. In effect, it's got to the end of the collection. So the next time we ask it, are there any more items in the collection for us to process, it's going to return false. So at this point, it's important that the iteration stops and that we do not call next again. If in fact we failed to respond to the iterator returning false from the hasNext method and then called next inappropriately, then the program would end with a runtime error. So it's very important always to protect any calls to the next method with a prior call to hasNext, and pay attention to whether the hasNext method returns true or false. One of the things that we've said about collections is it can be very tricky to process them and remove items selectively from them. And one of the reasons for introducing the iterator type is that it provides us with a safe and efficient way to process a collection that includes removing items. So here's our remove method from the music organizer class, where we wish to iterate through the collection and remove all of the tracks that are by a particular artist. And in this case, we're using an iterator rather than an integer index in order to do that. You can again see exactly the same pattern as we've seen in the previous examples. We request an iterator from the collection. We have a Boolean condition in the loop to check whether hasNext is returning true or false. If it returns true, we repeat the body of the loop, retrieve the next item, and then process it in some way. In this case, we ask the track for the artist, and then we compare the name of the artist against the one that we're interested in removing. If the two strings match, then we want to ask the iterator to remove the item that it returned most recently. So this is perhaps the trickiest part of an iterator to appreciate. We call remove on the iterator, we don't call it on the collection. And the fact that the iterator has already gone one beyond the object that it most recently returned doesn't matter. The iterator is able to remove the item that it previously returned. So the mechanics of how it does that don't matter to us. That's all hidden by abstraction. We can simply trust the iterator to remove the object from the collection that it returned most recently to us. So this is very powerful, and it provides us with a safe way of performing removal from a collection while iterating over the collection. Here's a further example of a task that we've seen previously. Previously, we saw the idea of searching through a collection using an integer index. This time we're using an iterator to search through the collection. So the structure of the method is exactly the same as we've seen previously. We're simply replacing the use of an integer index with the use of an iterator. So we have exactly the same setup. We ask the collection for an iterator object. Now we have two parts to the condition of the while loop. We only want to continue as long as there's at least one more item in the collection to be considered and we haven't yet found what it is that we're looking for. So this method is only interested in knowing whether there's at least one occurrence of the search title in the collection. So as long as the condition returns true, once again we ask the iterator for the next item. We then make the necessary comparison, and if we find what we're looking for, we set the searching variable to be false. Notice that there's no need to update an index or do anything else if we don't have a match. We'll simply go back around to the condition, check if there are more items to consider, and then repeat the process until either we exhaust all the items in the list or we succeed in finding what it is that we're looking for. So we've now seen several examples that involve either iterating over a collection using an integer index or using an iterator, and we can make some comparisons between the two different ways of doing things. So if we consider using a loop with an integer index, for some collection types, including linked list, that will be relatively inefficient. We also have to manage the index explicitly, and it's a very common programming error that people forget to increment by 1 the value of an index and end up with an infinite loop that simply keeps on re-examining the same object each time around. We've also seen that it's possible to make logical errors when using an integer index, particularly if we fail to recognize that removing items can mean that the indices of following items will change. In contrast, we've seen the use of an iterator object. An iterator object is efficient for all types of collection because each collection provides an implementation of iterator that is efficient and designed for the internal structure of that particular collection. An iterator will also be essential when the collection does not actually support indexed retrieval. So there are some collections which simply do not have a get method that takes an integer index. And in that case, we're going to have to use an iterator if we want to iterate through the collection. We've also seen that an iterator object allows us to perform correct iteration and removal without making the kind of logical errors that are very easy to make with an integer index. So as a review, we've seen that collection iteration is a very common programming task. It's something we do over and over again in lots of different programming situations. All collection classes provide an iterator that manages sequential access to the whole collection. And one of the important features of that iterator is that access to the collection will be efficient for all types of collection. We've also seen that iterative removal from a collection is managed safely by an iterator. So when we have an iterative task to perform on a collection, it's well worth considering using an iterator as the primary choice of mechanism for performing the iteration.